Okay, let's move on to example number 12, a retaining wall problem. So as usual, feel free to pause the video for a couple of minutes and we'll be back. Okay, so now we're back. We have an 8 feet wall retaining wall, and we have the friction angle, we have the gamma value of the dry sand that the retaining wall is retaining, and asking for the overturning moment per unit length of the wall due to the lateral earth pressure. So first of all, the first step we're going to do is we have to determine whether the wall is we should use the active lateral pressure or the passive earth pressure, right? So the potential movement of the wall is going this way, actively moving away from the soil. So if that's the case, then we are talking about an active lateral earth pressure. For another scenario is that if the wall is passively being pushed into the soil, then the soil pressure in that case is the passive lateral earth pressure. But for our case over here, we're talking about a active lateral earth pressure. To come up with the lateral earth pressure, we need the lateral earth pressure coefficient, and which is Ka. You can find the Ka in the reference manual. The definition of Ka is tangent 45 degree minus friction angle over 2 and squared. Our friction angle is 32 degree right over here, and the Ka is 0.307. So we have the Ka, and now the next one is we need to figure out the distribution of the lateral earth pressure. And we know for sure at the top it's going to be 0 because you don't really have any soil over there, so you don't have any vertical stress, so your lateral stress is naturally be 0. And if you can find another one at the bottom of the retaining wall, and we know the soil is uniform, so if you can find out the lateral earth pressure right over here, and the distribution of the lateral earth pressure will be basically a triangle kind of looking like this. The question is to find out how much this would be, right? Well, this is actually pretty easy. If you can, we know that this is the Ka is a factor or coefficient, whatever you call it, and as long as you can find it's a coefficient or factor on top of the vertical earth pressure. So basically, you have to come with a vertical earth pressure at this step, and then multiply that value by Ka. Then that would be the lateral earth pressure value. So first of all, we do the vertical pressure first. So at 8 feet, your sigma v, the vertical pressure, is basically gamma of the soil times the height of the soil or the depth of the soil, whatever you call it. That is 120 PCF times 8 feet, and you can get that number, or so that would be 960 PSF. So then the lateral earth pressure at that point is essentially the Ka times gamma times h, or the Ka times this whole thing is sigma v, 0.307 times 960 PSF, and you will have 295 PSF. So this value over here is 295. So now we have the distribution of the lateral earth pressure, then we can have the total lateral earth pressure force, or an equivalent lateral earth pressure force, and we can use a FH. Then your FH is basically the area of this triangle. And to come up with the area of the triangle, we use half of the height, which is 8 feet, times that 295 psf. And that is the lateral or the equivalent force. And that is 1180. The unit is pound per foot because we're only dealing with one section over here, and we're dealing with one unit length of the section. So for the moment, and we know the FH is about 1180, and the location would be a third from the bottom of the wall. And that third of the bottom of the wall is 8/3. So the overturning moment, we are typically considering the overturning moment point is here. So we're overturning this wall against this this toe location of the retaining wall. So based on that, the moment would be FH times a third of the total wall height. And you'll find the answer for this one would be 3146.3 pound times foot per unit length of the wall. So so the correct answer is C over here. Okay, so that's pretty much about it for this example number 12.